In today's video, we're going to be looking at significant tests. And tests of significance or significance tests are going to be techniques, tests that we're going to be using the rest of the semester. And they're basically our organized way of making statistical decisions about our data. So let's look at what the characteristics are of every type of a significance test, and then we'll look at the specific example that I have below. And we'll actually learn a number of different types of significance tests as we move throughout the rest of the term. But when we start a significance test, we basically have, in this chapter, we have the idea that there is a certain population that we're looking at. And we are going to make some type of an assumption about what is true about the population mean. For instance, we might be assuming that the mean of a particular population is, let's say we're dealing with the gas mileage that a car has. And let's say we might assume that the gas mileage that a car gets is 25 miles per gallon. So there's a certain assumption that we have, which we will call our H sub 0 or our null hypothesis. Then there will be an alternative hypothesis. Now, the alternative hypothesis might be something like we think the mean gas mileage is less than whatever we had assumed up here. So if I had assumed that the gas mileage on a car was initially 25 miles per gallon, my alternative hypothesis could end up being that I think alternately that the gas mileage is less than 25 miles per gallon. Or maybe I think it's more than 25 miles per gallon. Or maybe I'm not sure which way the direction is going. I'm not sure if it's higher than 25 or lower than 25, but I'm pretty sure it's not 25. So our alternative hypothesis can have basically three types of signs. These two would be called one-tail hypothesis test, and this, where I have not equal to, would be called a two-tail test. All right, so again, we have a certain hypothesis that we have the null hypothesis, and then we'll have an alternative hypothesis. These hypotheses, by the way, will always be written in terms of parameters. We might say that, assume that the mean of a population, a mu, not an x bar, a mu is equal to a certain number, and then alternately the mu is greater than, less than, or not equal to a certain number. Then we have a certain test statistic that we have that's basically based on our sample, and then we'll use that test statistic to find out how likely it is for the occurrence that we get from our statistics to occur in our simulation or in our data collection, or more extreme, and then that will cause us to calculate what is called a p-value, which will be a probability. So let's just start with the example. This happens to be the test statistic that we're going to be working with in this chapter, but we'll have, again, many other test statistics that we'll look at. And I'll get back to the idea of significance level in a minute. So let's look at our example. So we have the survey of study habits and attitudes is a psychological test that measures the attitude towards school and study habits of students. The scores range from 0 to 200. The mean score for U.S. college students is about 115, with a standard deviation of 30. It doesn't say anything about the shape of the distribution. A teacher suspects that older students have a better attitude towards school. She gives this test to 25 students who are at least 30 years of age. Those are considered our older students. The sample of 25 has a mean of 120.6. Do we have evidence that older students score better than the average college student? Assume that the scores for the population of older students are normally distributed with a standard deviation of 30. Okay, so now we're throwing in that we're supposed to assume a normal distribution. So the basic setup is this. We are going to assume that these college, or these 30 or older, these people who are 30 or older, we're going to assume that they have a normal distribution for their test score for this test. We are going to assume that they are no different from what the average college population is. We're going to assume that they will score 115 points on this test on the average, and that their standard deviation of these scores is 30. And again, that's for an individual student. Okay, so we could actually draw the picture of the distribution for individual students centered at 115. This is for individuals. and having a standard deviation of 30. So having this be 30 units this way, 30 units this way, etc. Now, in reality, they got an X bar from this population, got an X bar of 120.6. So what we should think of is if the mean is really 115, so again, that's our null hypothesis or the value we're assuming. If we take simple random samples of size 25, taking a sample size of 25, and that's a big enough sample size based on this population being normal, and actually, even if this population wasn't normal, our sampling distribution of X bars would be pretty close to normal based on the central limit theorem. But if I continue to take samples from this population, assuming that the mean is 115, if I continue to take samples of size 25, get X bars, X bars, X bars, etc., remember that's our sampling distribution of X bars, and we would anticipate that these X bars would center at 115, just like individuals. However, the standard deviation of these values would be expected to be smaller. It should only be the individual over the square root of n. Okay. So the sampling distribution should center here, have this standard deviation, and should be approximately normal for basically two reasons. Because the original population was normal, the sampling distribution will be normal, but also the central limit theorem says, it doesn't really even matter that this was normal because this is relatively large and your sampling distribution will have approximately a normal distribution. So I can draw my picture of my distribution. Now again, we're assuming that the mean is 115. That's what our null hypothesis is telling us. Now how likely is it to sample from this population that looks like this? Again, these are groups of 25 people, not individuals. And how likely is it to get a mean of 120.6 or higher? When we do one tail test, we always take the statistic that we get from our sampling and more extreme, which means away from the mean that we're assuming to be true. So we want to know how likely is this to occur if the population mean is truly 115 for these older students. So now we're ready to convert it to a z-value. The number minus the mean divided by the standard deviation of our sampling distribution, and then we can find what that corresponding z-value is, and then we can find that probability. Now, let's go back up to the terms that I talked about up before. This calculation that I did right here was actually taking the mean that I got minus the population mean that I'm assuming to be true, and then I divided by that standard deviation of individuals over the square root of n. This calculation is called my test statistic, and that's what I have written right up here. This is the test statistic that we're going to transform our sample compared to our assumed mean from the null hypothesis, and this will help convert it to the z-value, which is in turn called the test statistic for our hypothesis test. Okay, so if I asked you to calculate the test statistic, this is the number I'm speaking of, and it happens to be a z-value because we're dealing with a normal distribution. Now, I find the probability of this tail. This z-value is 0.93, and I get this probability. This probability in statistical language is called the p-value. Now the question is that unusual? Now, people could argue and say, oh, that only happens 18% of the time. That doesn't happen all that much. Or someone could say, yeah, that happens 18% of the time. That happens quite often. So the meaning of this value is that if the population mean from our null hypothesis is really 115, this p-value tells us the likelihood that you'll sample 25 numbers, find the mean of 120.6 or higher. That's how often that will happen in this distribution. Now, is that unusual? That's where this idea of a significance level comes in. The idea of a significance level is a judgment that you're basically pre-given about what will be considered to be unusual or statistically significant or not. Significance levels are common at 5%, 10%, and you can go as low as 1%. You could actually go lower than this or higher than this, but those are fairly typical significance levels. And what they mean is a question may be worded something like this. You could be given this problem and you could be asked, do a hypothesis test using a specific significance level. And the way I like to think of a significance level is like a little bar. And I think of, okay, here is a p-value, and we're looking at what the p-value is for this setting. Let me get some lead here. And in fact, we'll just switch pencils since that lead does not want to come out. And a p-value of 0, where the probability is absolutely 0, is our lowest we could possibly have. And we have a certain significance level. And let's say I said to use a significance level of, let's say, 10%. That would mean, and a significance level is signified as an alpha level, that would show me that this alpha level of 10% or 0.1 is basically my cutoff point where I'm going to say something is unusual or where, oh no, that's just normal variability. So if I were doing a hypothesis test and I calculate a p-value like this, I always compare it to the significance level if it's listed. So if I had said it's a significance level of 10%, anything that has a p-value that is less than 10% would be considered unusual if the mean that you're assuming to be true is true. So we're saying it's not very likely that this would happen to get this type of a value if your actual null hypothesis is a true statement. On the other hand, if you get something compared to your significance level that is greater than or equal to the stated significance level, then this would just be considered normal variability. Normal variability for distributions with a mean as assumed to be true. So if you get something that is less than your significance level for a p-value, that would be considered evidence against your null, or that would be considered unusual for the null if the null were true. So on our scenario here, if I used a 10% significance level, I would look at this picture and go, well, the likelihood of getting a 120.6 or higher, that happens 18% of the time. Now I look at my measure. That's up here. I guess that's just normal variability for a distribution that's centered at 115. You're not going to always get 115 when the distribution is centered at 115. When you sample, sometimes you're going to get higher, sometimes you're going to get lower. So I would say this is not unusual, and this is cut off here a little bit. I would say we do not have evidence against the null. The null seems to be true. So that's what we're looking at when we do a hypothesis test, is we're trying to find, do we have evidence to say, nope, that's not true. And if it's not, doesn't seem to fit the circumstance, and it doesn't seem to be true, I guess I need to move this down so you can see, we're trying to find evidence against this value. And if our variability for the p-value comes out to be higher than our p-value, then we say, no, we don't have evidence against the null. That's just normal variability for a distribution. However, if you get a p-value that is less than your significance level, then we would say, yeah, that's unusual. So we would have evidence against our null and think that the alternative is true. So let's turn over. So now we're going to do something that is quite similar, but we're going to go to a gas mileage question. The average gas mileage of a specific brand of car on the highway is 26 miles per gallon with a standard deviation of 2 miles per gallon. The car has been remodeled or updated somehow, and the manufacturer wants to determine whether the gas mileage has been affected by these changes. The engineers take a sample of 30 cars. So let's stop a second before I even read the sample size. It used to be that the gas mileage was 26 miles per gallon, and we had this standard deviation. Again, we're not told anything about the shape of the distribution, probably a normal distribution, but it doesn't say anything about the shape of the distribution of individual cars. However, I don't know what effect this updating has done. I don't know if it's increased my gas mileage, decreased my gas mileage, or maybe it hasn't done anything at all. My assumption is automatically going to be my gas mileage has not changed. That would be my null. Okay? And alternately, since I'm not sure whether it improved or made my gas mileage worse, my alternative would be that it's not equal to 26. So these are my null and alternative hypotheses before I even look at the rest of the question. I know that's what I'm going to assume the gas mileage is, and I know that's what I'm going to assume the alternative is. And remember, these are never x bars here. These are always parameters. You don't put an x bar in a null hypothesis ever, ever, ever. Okay, so now what did the engineers do? They took a sample of 30 cars, and they measured the gas mileage of each of these vehicles. Now, we hope they were used a simple random sample. We hope they didn't go and try to find some cars that they think are going to be better or worse and so on. And when they did, these cars had an average gas mileage for those specific 30 cars of 24.2 miles per gallon. This should be. And now the question is, do we have evidence that the gas mileage has changed? It doesn't say anything here about has the gas mileage gotten better or worse. It's just has it changed, and that's another key word we look for because that's going to denote that we're going to do a not equal to. So you have to read the wording of the question carefully. And if it says something about did it change, is it different, then this will be a not equal to, as opposed to if I had said, do we have evidence that the gas mileage got worse? And if we had the word worse here, this would be a less than 26. Okay, so we have a sampling distribution. Now, we only took one sample, but if we think about, we're assuming that the population has a mean of 26 miles per gallon with this standard deviation for individual cars. We don't actually know the shape of this distribution, but we are taking random samples of 30 cars and finding a mean. So our central limit theorem would tell us that if you continue to take x bars, find x bars each from a sample size of 30, that sampling distribution of x bars will be approximately normal, and it will center at 26 miles per gallon with this standard deviation. So definitely using the things that we learned in Chapter 9. Now, I drew a picture here. And I'm showing 26 miles per gallon in the center, and I went out one standard deviation on each side, roughly 0.4 miles per gallon. And I know the sample, the x bar that was obtained, was 24.2 miles per gallon down here. There's the 24.2 miles per gallon. We always find that value and more extreme, so we find a tail. That's the upper tail. But you can also see that I'm finding something else, and this sample never came up. But what we do when we have a not equal to is we think of this kind of a context. If you have 26 miles per gallon and you don't know, you're assuming that the gas mileage is 26 miles per gallon. And if you sample, you know sometimes you'll get below that and sometimes you'll get above that. And we are, again, assuming that the gas mileage is 26 miles per gallon. So this sample that happens to be, 1.8 miles per gallon lower than the mean should be just as likely as being 1.8 miles per gallon higher. And that's at 27.8. So we actually not only find this, but we also find this upper tail, because this is called a two-tailed test. That's what our alternative hypothesis of not equal to is going to mean. So now I'm ready to go through and find my p-value. So I have my hypotheses. I drew my picture. I look at what I got from my sample. And if it's a two-tailed test, which means, again, the not equal to, I'll be finding actually two tails. And now I need to convert this statement to a test statistic, which I take the number minus the mean I'm assuming divided by the standard deviation of the sampling distribution. And remember, our test statistic is always going to be what we got minus what we're assuming divided by the standard deviation over the square root of n, and this is really the standard deviation of our sampling distribution. And this is coming up with our test statistic. Now, you can see that I did something here where I only put it 2 times. This lower tail and this upper tail are symmetrical. So all I'm going to do is find the area below this number and double it because I'll have the same probability in each tail. This number is my test statistic for my hypothesis test, and now I need to calculate the p-value. So I found this area using my normal CDF, which is basically extremely close to 0, and the other tail is also very close to 0, and it comes out technically to be this value. And look at all those zeros. Very, very small probability. If you put approximately 0, I would have absolutely no issue with that. It's not 0, though. It's just approximately 0. Now we go back and we look at our significance levels. We are actually asked to do this hypothesis test at 2 significance levels. And again, think of that little bar. The lowest p-value you can have is 0. We're using initially a significance level of 5%, and we look at where does our p-value lie relative to this little bar. And our p-value came out to be tiny. It's very close to here. It's extremely unusual to get this type of a value, or more extreme, or this type of a value, or more extreme. That only happens a fraction of a percent of the time. So this is very unusual if the true mean is actually 26 miles per gallon. So we definitely have evidence that this is so unusual that we would have evidence against the null. We have evidence against the null at a 5% significance level, but also at a 1% significance level, because here's 1% significance level. And definitely our p-value is smaller than a 1% significance level statistic as well, or bar, a measure. So we have evidence against the null, which means we conclude that the gas mileage has changed. Now, we don't say that the gas mileage for the cars has dropped down to 24.2. All we say is that the gas mileage has changed, because that's all we were doing in our test, is trying to find evidence that it changed. Now, if they wanted to go back and prove that the gas mileage has actually gotten worse, they would continue to do more testing and do a different hypothesis test. Okay, now the last thing we want to look at is this little last example here. And this last example is an idea that sometimes we can use a confidence interval to answer a question if we're dealing with a hypothesis test that is a two-sided or two-tailed test. So if we have a question, well, let's read this question. I have a computer. I'll move that up. A computer has a random number generator designed to produce random numbers that are uniformly distributed on an interval from 0 to 1. In other words, it's like our RAND button on our calculator. It spits out random values from 0 to 1, and our density curve would look like this with the area of 1. And this distribution has a mean of 0.5 and a standard deviation of 0.2887. Now, a command to generate 100 random numbers, so we could do RAND and then have it generate 100 numbers, produces a mean value, so this is for 100 numbers. You get an X bar with this calculator or with this random number generator of this. And it says assume that the population mu stays the same, or excuse me, sigma stays the same. And we want to find out, do we have evidence that the mean is no longer 0.5, or that this machine actually is not working properly? It should generate numbers where the mean is 0.5. We got an X bar of 0.4365, so do we have evidence against the no? So one way to do this test, and let me show not the confidence interval way, let me show the traditional way of doing hypothesis tests, would be to say, all right, well, I'm going to assume that the mean is actually here at 0.5. Alternately, I think it's different. So what did we get? Oh, we got a 0.4365. Now, since we're doing a not equal to, this number that is symmetrically located on the other side would be considered just as common. So the traditional way of doing the hypothesis test would be able to say, okay, let's find the likelihood of getting an x bar that is less than or equal to 0.4365. Now, I can also write, as I did on the previous question, and then go plus, and then figure out what this value is up here, which looks like it's going to be about 0.4635, I think. But we can also just double this, because this tail and this tail are going to be the same. And so the area below this number and the area above that number, when I add them together, is going to be the same thing as 2 times this lower tail. So now I'm ready to find my test statistic. And I find my test statistic, I would take that 0.4365 minus 0.5 divided by, and I would take my standard deviation over the square root of n. And 0.2887 over the square root of 100. And then I would convert that to the test statistic and do the arithmetic on it. Let me quick do that. I hadn't done that ahead of time. So I have 0.4365 in my calculator minus 0.5, and I'm going to divide that by, and that's 10, so this is going to be 0.02887. And when I do that, I get negative 2 point, and it comes out to be 1995. Okay, and now I'm going to find, with normal CDF, I'm going to find this area, which I can see is going to be relatively small. And I'm typing in my normal CDF. I'll just kind of scooch the calculator here. I'm going to plug in negative number, comma, second entry, or second answer. And then I need to double that. Okay, so now I'm getting a p-value of 0.0278. Okay, so now I'd actually be able to answer my question at this point based on doing the traditional hypothesis test, which all in all, I actually prefer this method that I'm showing you right now over what I'm going to show you next. But I want to use a 5% significance level. So I would look at this and go, okay, I remember that bar. Here's 0. Here's a significance level of 5%. Oh, I'm down here, which means this is considered unusual. So I could say I have evidence against my null, what I was assuming to be true. It looks like this mean is not right, and that the actual computer generator is not producing numbers that are centered at 0.5. So I would have evidence to show that I do not have a generator that's giving me the uniform distribution of spitting out values that are randomly numbers from 0 to 1. Now, here's the alternate way. The alternate way is to think, hey, let's do a test where we find a confidence interval. So we know that we have some sample that we got. We got an x bar of 0.4365, and I want to find if my significance level is 5%, 100 minus 5% means I want a 95% confidence interval. Now, this is only appropriate to do this type of a test if we're doing a two-sided test. So I've got my x bar plus or minus the 1.96. I've got my standard deviation over the square root of n, and I calculate my interval. So my confidence interval, remember, is an interval estimate for where I think my population mean is. And so here's what I got, plus or minus the margin of error, and this is where I think the mean is of the population for the random number generator. And I look at that interval and notice that 0.5 is not contained within my confidence interval. So it appears as though since 0.5 is not in my 95% confidence interval, we would have evidence against the null. And we would say, no, we don't think the mean is 0.5. So if I'm given a specific significance level, and I'm doing a not equal to, I can actually perform a confidence interval from my statistic, x bar plus or minus the level, take my significance level away from 100%. That would be the confidence level I would use for my confidence interval. And I can calculate a confidence interval and I can test to see, hey, is that center that I'm hoping it's centered at, is it within here? And if it's not, you would have evidence against the null. Now, if I change the significance level to 1%, this method is a little bit of a hassle because I would have to go back and I'd have to go refigure my confidence interval. And so the only thing that would change would be I would use a 100 minus 1%. I would look up the Z star value for 99% confidence and do the calculation of the interval. Now notice that now, since 0.5 is contained in this interval, we would say that we don't have evidence against the null. This seems to be consistent with variability that would happen for a 99% confidence level or a 1% significance level. Now, the nice thing about doing a hypothesis test this way is this p-value can be tested in one calculation against any value. If my significance level had been 1%, I would have said, no, I don't have evidence against the null because my p-value is up here. If I have it at a 5% significance level, I can say, oh, yeah, that's low, that's unusual. So, as I said before, I really prefer to do all hypothesis tests with this technique, with just finding what my setup is with my sampling distribution picture, converting my number to the test statistic, finding the corresponding p-value, and then testing it against the significance level. Because in this case, I can test this p-value against any significance level, and I have no more calculations to do. As opposed to here, if I have differing significance levels, I have to recalculate different confidence intervals using a different Z-star value depending on which level of confidence. However, these are appropriate ways to do tests if and only if this is a not equal to setting. That's been a 32-minute video, and I think it's time to practice.